Mic check. Okay, there you go. It's working. So hello. Today we're going to be doing numbers 9 and 10 for homework. For homework 1 of radioactivity half-life. All right. So this is number 9, and I already wrote out all the work ahead of time. So if you take a look right here, we know that T is 6,400 years as given to us right here. That's the time that passes. We're solving for the half-life. That's the answer here. NT is what is left, which is also given to us because we know that it's only 6.25%. And then the easiest way to solve for this would be to plug in values as to what the original might be, right? So if you know what's left is 6.25% of it, then you can, if you assume that it started with 100, you have 6.25 left. You know, it's the easiest way to do it. And then from there, what I would do is that I would use this formula first. NT equals NO, or N origin, over 2 to the power of T divided by T half-life. So the next step, I would just move this, switch this and this, switch places because we're solving for T half-life. So we want to get that on the other side. From there, you can plug in values here to solve for this ahead of time, or you could just leave it until the end. But I just solved it here, plugged in values here to make it easier for myself. And then to get rid of this 2, what I do is I take log of each side. This side I take log of 2, and this side I take log of whatever this equals to, which is 16. Right? And then from here, I move this log 2, I divide it over to get rid of it on this side. In which I end up with T over T half-life equals 4, right? And since we're solving for T half-life, what we would do first is to multiply it over to get T by itself. We know what T is, as given to us right here. So then I would plug T in, and then once T is plugged in, I just divide 4 over, and I get 1,600 for T1 half. The second method of solving it with the same thing is if you keep note of this, this second formula right here, NT equals N origin e to the power of negative rate times time. So what I would do here is I would move this over. That's the easiest step to isolate for this. Now once you get to here, we already know these values, so if you wanted to, you could plug this in right then and there, but since I want to save myself the work, I just leave it and then I do it at the end. To get this down, because it's an exponent of e, I would use natural log to cancel out this e, because natural log perfectly cancels out e. So at that point it becomes negative kt over t equals natural log of that, pretty much, whatever you get that out to be. At the end here, I plugged in for t, because then, I divide both sides by t to get rid of it here. And then at the end, I plugged in for t. I plugged in these values here, and I just punched it in the calculator. And what you would get is 1,599.66, which is relatively very close to this. So, that's how you know it checks out. For the next one, let's see if this will work. Alright, I hope it went over. Okay, cool. So, for the next one, this is number 10. We'll be looking at, during the accident, the radioactive isotope of iodine, right? It gives us the half-life, which is 8.040 days. So right here, as you can see, I wrote down the half-life, and then it asks how long did it take for it to be reduced by 1%. Which means that after from the iodine to be reduced, as in 1% is left, right? So then the same thing we did for before, since we know that it's asking how 1% is left, and you can assume that 100 is the original and 1 is that's left, because then 1 out of 100 is the same thing as 1%. Now, once you get to that point, once you have all these values down, you can move on to the formula, which I used as the same as the other one. NT equals NO over T divided by T1 half, 2 to the power of T1 half, right? Now, what I did here is that I switched these, like I did with the other one, to turn it into this, right? T1 half equals to n over nt. I plug in values here. This is 100 over 1, and that's easy math because you know that that's just 100. So then in order to get rid of this 2, you take log of 2 here and take log of 100 here. At that point, we're reduced t over t 1/2 equals 2, which is log of 100. And then to get rid of this, I divided it by log 2 to move it to the other side. And then I multiplied 8.4 over, right? Because we know that as the half-life to be there. And then for your answer, this is what you get. Now, moving on to the second method of solving it, this formula, this is the other formula that we used the other time as well. The amount left equals the original amount times e to the power of negative rate times time. At this point, we're solving for t instead of k. So what we do first is we have to isolate for e. So by dividing n origin over, you can get e by itself. But at this point, we come to that same problem again where we're working with e instead of the actual exponents which we're looking for. So in order to solve for that, we just take the natural log of both sides. Natural log of e cancels e out. So then you could just rewrite this as negative kt. Whereas the other side, you need natural log of 1 over 100. From here you move on to this. I just plugged in some values. So what happened was I took natural log of that, which turned out to be this, and I divided k over, negative k over, which is this, right? Because k is equal to 0.693 over t half-life. And then we're given the half-life right here. See? So then after doing that math, then you just punch in the calculator, and this is what you get for t. And by a quick comparison, you can see that you got the right answer. Alright, thank you for watching.